Hi there, folks. We're going to take a few minutes and talk about the intermediate value theorem. This is an important theorem. We'll be using it later on in the course to prove some really big results. Unfortunately, it's one of those theorems that gets into the nitty-gritty detail about what it means to be a real number and properties of the real number line. So we don't quite have the tools in this class to really talk about the formal proof of it. That being said, we can certainly talk about why it's true based on our understanding of continuous functions. So the intermediate value theorem says the following. You've got a continuous function f on an interval containing real numbers a and b, and d is any real number between f of a and f of b. Then you're guaranteed at least one real number c between a and b with f of c equals d. Now that's a whole alphabet soup of letters there, which is why, let's think about this graphically. Once again, every big result in this course, you've got the words, but you also have a nice picture. So first off, we're going to assume f is a continuous function on an interval containing real numbers a and b. So here we've got the graph of f. It contains numbers a and b. It's defined on the interval. So here's a comma f of a, and here's b comma f of b. And the fact that f is continuous means that when we go to draw the graph of f, it's a nice connected curve. Okay? There's no jumps, there's no gaps, there's no holes in the graph. It's a nice connected curve. So here's where the word intermediate comes into play. When you see the word intermediate, it means something in the middle. So d is any value you want between f of a and f of b. So think of d as the intermediate y value, or d is the intermediate function value. So let's go right here. Then the intermediate value theorem guarantees that there's some intermediate x value, c, that goes with it. So that d is equal to f at c. So what's a real world application of this that makes sense? Let's say at 8 in the morning it's 30 degrees Fahrenheit, and by noon it's warmed up to 40 degrees Fahrenheit. So we kind of assume that the temperature is a continuous function, which means it's going to go through every temperature between 30 degrees and 40 degrees as you go from 8 to noon. So for example, the intermediate value theorem would say you're guaranteed that at some point between 8 a.m. and noon, the temperature was exactly 37 degrees. So that's the intermediate value theorem. If you have a continuous function on an interval, intermediate y values come from intermediate x values. And so here's a classic application of this, is when we're trying to solve equations. So let's say we were trying to solve an equation here. Let's say we were trying to solve an equation, x equals cosine of x. All right. Then that's equivalent to solving the equation x minus cosine x equal to 0. So every equation ever that you want to solve can be written equivalently as trying to solve an equation equal to 0. So I'm going to let this be my function f of x. Now x is a continuous function, cosine of x is a continuous function, and I'm just taking the difference of continuous functions. The difference of continuous functions is continuous. Combinations of continuous functions are continuous. So let's take a look at f of 0. So 0 minus the cosine of 0, that's negative 1, and f at pi over 2. That's pi over 2 minus cosine of pi over 2, which is pi over 2. Now what I'm looking for is I'm looking for a place where the f of x is actually equal to 0. At 0, I've got a negative function value. At pi over 2, I've got a positive function value. So if I think of what's going on graphically here, at 0, I've got a negative value. At pi over 2, I have a positive y value. Since the function's continuous, I know I've got to connect the graph with a connected curve. Or connect these points rather with a connected curve. So I know that somewhere in between there's a place where the f of x actually equals 0. And so by the intermediate value theorem, I am guaranteed at least one solution to f of x equals 0 in the interval from 0 to pi over 2. So let's fire up Desmos to see this. So let's look at f of x equal x minus cosine x. And let's specifically look at from 0 to pi over 2. And so we can see there's that positive right there in the middle, somewhere around 0.739-ish. All right. Now notice that's the same place as if I graphed y equals cosine x and y equals x. They intersect right there at 0.739-ish, and that's exactly where that x-intercept is for that function. Okay. So the intermediate value theorem is what we call an existence theorem. It tells you that there's an answer, but it doesn't tell you where that answer is. That being said, we can use the intermediate value theorem iteratively to help us narrow in on where that solution is. And so this is called the bisection method. So the bisection method says this. So we've got our function f of x, x minus cosine x. We're trying to solve f of x equals 0. I know I've got these two data points, 0 and pi over 2. At 0, I know that the function's negative. At pi over 2, I know that the function is positive. So what I'm going to do is I'm going to bisect or cut this interval in half, say at pi over 4. And now I'm going to look at what f of pi over 4 is. So that's pi over 4 minus the cosine of pi over 4. And we'll go ahead and use Desmos to help us with this. So f of pi over 4 is, well, 0.078 blah, blah, blah. Well, that's a positive number. So this is a positive number. So that's a positive number. So that means if I'm looking for where the function is 0, I'm not guaranteed we've got something over here, but it's going to have to happen between 0 and pi over 4 because that's where we change sign from negative to positive. So I know the 0 has to be in here somewhere. So now I bisect this interval. So I look at pi over 8. And I look at f at pi over 8, see what kind of number that gives me. So f at pi over 8, look at that. It's a negative 0.53, etc. So that's a negative number. So that tells me that the 0 is going to be between pi over 8 and pi over 4. So then I can continue this process. I can chop that interval in half. What would that be? Well, that would be the midpoint of pi over 8 plus pi over 4. So pi over 8 plus pi over 4 would be pi over 8 plus 2 pi over 8, which is 3 pi's over 8. And then cut that in half. That's 3 pi's over 16. I can look at f at 3 pi over 16 and see if that's a positive or a negative. Oops, did I? 3 pi over 16, rather. F of that is a negative number. So that's at 3 pi over 16. Which means then I could now chop this interval in half, etc., etc., etc. So you can see how we're narrowing down the x-coordinate of that x-intercept. We started off knowing it was between 0 and pi over 2, and now we know it's between 3 pi over 16 and pi over 4. So just to show you, 3 pi over 16 and pi over 4. So we know it's between these two numbers. And I could keep doing, I could keep doing that method, right? And I would slowly narrow down where that x-intercept is. Okay? So it's a very methodical process. Typically it's a very slow process, but we're using calculus properties, aka continuity in the mean value theorem, to help us narrow in on that x-intercept. Now in the next chapter, we're going to have access to more powerful calculus tools that's going to help us zoom in on this answer a lot faster. But for now, we've got continuity in the intermediate value theorem.